Here are the homework answers from last night. Problem 1, and it's part A. So the problem set up was in the classic novel Don Quixote, the title character famously battles a windmill. In this problem, you will model what happens when Don Quixote battles a windmill and the windmill wins. Suppose the center of the windmill is 20 feet off the ground and the sails are 15 feet long. Don Quixote is caught on a tip of one of the sails. The sails are turning at a rate of 1 counterclockwise rotation every 60 seconds. So there's the setup, and you had that to look at. Therefore, if it is 15 feet for this sail, and it is 20 feet from here to there, what is the leftover distance at the bottom?
5 feet.
5 feet, right. Okay, so we'll come here to problem A. Explain why a sine function could be used to model Don Quixote's height above the ground as a function of time. Now, as we've learned, some of these answers are long-winded, but here you'll get the main idea from this. Since Don Quixote is moving around a circle and the sine function measures vertical displacement of an object moving around a circle, we can use a sine function to track his position above and below the horizontal line through the center of the sails of the windmill. You could have just said a sine function tracks the movement around a circle. That would be an easier way of saying that. All right, here's part B. Sketch a graph of Don Quixote's height above the ground as a function of time. Assume t equals 0 corresponds to a time when he was closest to the ground. So it starts at the bottom, and you notice closest to the ground means he's at 5 feet right here, and I'll zoom in a little bit better so you can see that. Starts at 5 feet there, and he's moving all the way up. Remember, the sails are 15 feet each. So 15 and 15 is 30. That is going to take us up here to 35. 5 feet off the ground here, all the way up to 35, then back down, and so on. The difference between 35 and 5 is 30. Half of 30 is going to be 15. So if we go look at 15 in here, half of 30 is 15, so we add the 15 to the 5 to come up with 20. So there's your midline all the way through. All right, and it says, what are the amplitude, period, and midline of the graph? Well, we just drew the midline at 20, so that's where this comes from. Y equals 20. And then, as far as the period, remember the formula I gave you way before that break that we went on? It's going to be 2 pi over the amount of time it takes it to go through one rotation. And since this is in terms of seconds, then it's 2 pi over 60 there, which is the same thing as pi over 30. And of course the amplitude is 15 feet. Here's 1C. So model Don Quixote's height h above the ground as a function of time t since he was closest to the ground. Okay, there's the function given to you there, but I'm going to explain to you how we came up with it. And we're going to start here with the initial graph, where let's say he was a passenger car on a Ferris wheel, and let's say he started here at 0. Well, he's going to go up to 15, down to negative 15, and so on. Remember, the sails are 15 feet long. So that would be 15 sine t. We're building it from scratch. All right, we'll go down to here and add in something else. Now, if he's at 5 feet off the ground, and the distance from the ground to the center of the windmill is going to be 20, then we're going to add a 20 here at the end. Remember the Ferris wheel yesterday, the distance from the ground to the center was, I think, 40. So we added 40 at the end. When we add 20 at this end, it bumps all the points up 20. And it moves this midline to 20. There's your midline. There's the 20. So we're saying he's starting off at 20, which we know is not entirely accurate, but we still have to build on to this to get to the accurate function. So 15 sine t plus 20 is where we're at now. And then down here, here's how you get the rest of it. Notice back up here where this was at. This one. And we want him to start at 5 feet. See, here's a minimum at 5 and at 5. Notice that I would have to move this graph over 15 in order to get this piece here to line up at the 0. So if I move it to the right 15, then this is where I get the minus 15 from, to go to the right. And then the pi over 30, remember back at the beginning of the problem where it was 2 pi over 60 seconds? The 2 pi is part of the formula, and the 60 seconds came from the amount of time it takes for the windmill to make one rotation, 60, so I reduced that to pi over 30, and that's where you put it here. So there's your amplitude, there's your W, there is your minus 15 phase shift, and there's your plus 20, and here is the graph of that windmill problem. 1D for this problem. After 1 minute and 40 seconds, Don Quixote fell off the sail and straight down to the ground. How far did he fall? Okay, so he fell at 100 seconds. The vertical distance in feet that he fell is the following. We're putting in 100 seconds for t, which is right here. So you have this minus this, and it comes out to be 100 minus 15, which is 85. And then we have the plus 20, the 15 sign there as well. Question, can you figure out how they have arrived at 2 pi and the 5 pi over 6? All you have to do is type it into your calculator and make sure you change it to radians, and you'll come up with 27.5. On problem 2, did any of you notice anything strange? If you went to look at the lesson plan that I posted on the web page. Did anybody look at the lesson plan I posted on the web page, which has the homework answers on it? No? Okay. You didn't notice anything strange. Here's 2A and 2B. The High Roller Ferris wheel in Las Vegas, Nevada opened in March of 2014. The 550-foot tall wheel has a diameter of 520 feet. From that point in the problem, if you had looked at the lesson plan and the answer key to check your work, you would have noticed something strange. I'll ask you that since the Ferris wheel is 550 feet tall and has a diameter of 520 feet, what should the leftover distance be at the bottom, like the platform they're using to get on the Ferris wheel? 30 feet, yes. If you had looked at the lesson plan, as I did, and that's where I get the solution guides and make some changes to them, they have the wrong solution altogether. They have a difference of 20 feet, and that I went through and redid their stuff to make sure that the 30 feet was accounted for. And you'll notice here in their graph, it may not be easy to tell, but they're starting at 20 feet down there. Hard to tell the difference between 20 and 30 feet that small. And they've gone up to, let's see, we had the diameter is 520, and then they added 20 to that, so they go up to 540, and that's not right. And look at their equation. They have a plus 280 there at the end where they've added 20 to the 260. That isn't right either, and I've changed that as we go through the problem here. Okay, and the other important piece of information was assume that once the wheel is in motion, it maintains a constant speed for the 30-minute ride and is rotating in a counterclockwise direction. 30 minutes to make one rotation. Oh my. Okay, well here it is. There's the wheel. It has a radius of 260. That's half of 520. The distance from the very top down to the ground is 550, so that's a difference of 30 feet. They had 20 for some reason. That's the setup for the problem. So I started from scratch, and I figured that since the radius is 260, we should start with 260 sine t. t in terms of minutes. That's what the graph looks like, up to 260, down to 260. And then what I've done there is added 290. Remember, the 290 will come from the 30 feet for the platform or whatever they're using to get on at the bottom, plus the radius. So you add the 290 at the end, then it bumps everything up 290. That means you're starting here at 290, and that means that your midline is 290 from there. And then next, I've added in everything else. Now, look what I had to do. We have to start this thing down at 30 feet. Here is 30 feet down here. That's as low as it'll go. To start it at 30 feet at 0 over here, I had to move this over at least one column. And one column is represented by 7.5 minutes. Here's 15, here's 30. Halfway between those two is 7.5. So that would be 22.5. There's 7.5. And if I have to move it to the right 7.5, that's where this comes from here. Right there. Okay. And then remember how you get this? It is 2 pi over the amount of time it takes you to make one revolution. So 2 pi over 30 reduces down to pi over 15. And there is your graph. Explain how the parameters of your sine function relate to the situation. Well, the amplitude is 260. That's the radius of the wheel. The period is 30 minutes, so you do 2 pi over 30 to get that w in your sine function. You reduce it down to pi over 15. The midline is not 280. That's incorrect on their solution guide. It should be 290, and it just disappeared. 290. And then what else do we have in here? That represents how high the center of the wheel is above the ground. And to make the graph have a minimal point at t equals 0, the shift can be 7.5 to the right, which corresponds to 1/4 of the period. If you were on this ride, how high would you be above the ground after 20 minutes? So in this function, everything is right except this. That is 290. And of course, the final answer will not be right. So plug that in. Your calculator should still be in radians, and if you did not listen the first 2 times, it was mode, and then tap on radian, and then plug in what you see here, 260. We have to do it anyway to get the right answer since the key that was generated is wrong. 260 sine, and then you're going to have to put in a parenthesis after that initial parenthesis. And you can put pi over 15. Second caret is pi divided by 15. Close that quantity and then put in another quantity of 20 minus 7.5. Close that quantity and then close again. And we should come up with a plus 290 at the end of it. Okay, so what do you come up with for a final answer? I came up with 420. Yeah, it should be 420. Did you change yours to radians? To plug this problem in your calculator, I said 260 sine. Here's the parenthesis that automatically goes in. I said we had to put in another parenthesis and do the pi over 15, which is the reduction of 2 pi over 30. And then close that off and multiply it by another quantity, which is 20 minus 7.5. So we close that quantity and then the other one. And then you have to put in plus 290. You should come back with an answer of 420. For 2e, suppose the ride costs $25. How much does 1 minute of riding time cost? How much does 1 foot of riding distance cost? And how much does 1 foot of height above the ground cost? Okay. Well, in this problem, they've done 25 over 30, which equals 5 over 6. So 1 minute of riding time costs 83 1/3 cents. That shouldn't change because it's going in terms of minutes. So you should still have 83 and 1/3 cents. And that comes from a basic math calculation. The circumference of the circle is 520 pi feet, so that has nothing to do with the height of the wheel on the top to the ground. Dividing 25 by the circumference indicates that each foot of ride costs about 1.5 cents. And the height of the Ferris wheel is 550 feet. Dividing by 25, and that's not going to change either. Remember, it is still 550 feet above the ground. So dividing 25 by 550 indicates that each 1 foot above the ground costs 4.5 cents.